We had the conservation of mass. So that was our first fluid flow equation. Remember, it's one-dimensional steady state flow. Why is it 1D? Because the pressure and density only change in one dimension as it goes down that pipe or that duct. Why is it steady state? Because they don't change in time. So this says rho at one point is equal to the same thing at another point. Or you can think of this as like a conservation law, because it says anywhere in the flow, this combination of variables is constant. So when you multiply all three of these together, that quantity, which is mass flow rate, is conserved. And that's why we call it the conservation of mass. Yeah. Yeah. And then the next assumption is we can say incompressible flow. And you may think, well, gosh, I got to keep track of all these assumptions. Again, like I said last time, you got to pick the right equation for the right situation. And so you need to state the information that led you to choose that. Yeah. Conservation. My mistake, not yours. It was crappy writing. All right, so this is another assumption that we can make. And the idea here is that if we squeeze a substance, which really means if we put a force on it, put some kind of force on it. How about if that substance is steel? This is a steel beam. I'm pushing on it. Is it changing its shape at all? Is it compressing? Well, actually it is, right? But I'm probably bending this a negligible amount, right? So we could assume that this force on this beam is so small compared to the elasticity of the beam that it's not really deflecting at all. So steel, if we had a cube of steel, imagine how much force you'd have to put on that steel to compress it down. Because it's in a solid form, so all of the atoms are linked in that crystal structure. You actually have to physically push the atoms together in that, and it's really hard to do because the electrons are shared between each of the atoms. And so this is hard to compress. How about water? Still not very compressible. It's a liquid, but even in its liquid form, the atoms are pretty close together. And so to push those atoms even closer together takes a lot of force. Can't say it wouldn't happen. I mean, in steel, you can compress, put it in the interior of a star, it heats up, it melts, you can compress it. Still hard. So if we're having a problem where we're dealing with an airplane, which would really be a submarine in the water, we could pretty much assume incompressible. Okay, how about air or gas? If you take a balloon, imagine going to Party City, one of those Mylar balloons. If you push on it, it wiggles around, but how well could you compress that down into a volume half its size? it would still take quite a bit of force, wouldn't it? You could do it because the gas is more compressible, so you need large pressure forces. So we have to make a decision as, well, when do we have to say a gas is compressible and when do we say a gas is not compressible? And the whole idea here is that if we can say the density in this equation is constant, then that's an unknown that we can throw away. We don't have to worry about. All right, somebody tell me where I put my eraser. Oh, geez. You know what this blackboard really needs? The tray on it, right? Maybe I should buy one. Go to the department and say, I need a tray. All right, so it'd make it look less classy. Yeah. So who should I blame for buying these whiteboards that don't have trays? No, actually, I did it. Some of the other teachers that teach in here wanted whiteboards, and these looked really cool. I just didn't notice that they didn't have trays. So I need to fix that. All right, so if we have compressible flow, then rho varies. Whereas incompressible, rho is constant. So in that equation, we can say rho 1 equals rho 2, and we can cancel. We don't just write the equation down without rho in it. I want you to write this equation down, and then if you assume incompressible, write well, you could say assume incompressible flow, and then cancel the densities out, because then you remember you did that. Not only that, but you remember this equation, so if you ever have to do compressible flow, you don't accidentally get the wrong equation. All right, so the rule of thumb, and we'll justify this later, but the rule of thumb is if the velocity is less than 100 meters per second, that's easy to remember, 100, right? A century of meters per second, or about 225 miles per hour. And all of these are really based on that they're about less than 3/10 of the speed of sound. And why the speed of sound? The speed of sound is related to pressure disturbances. So this is related to how much speed you have that can compress the flow due to the pressure forces pushing in on it. All right, how are we doing on time? 12:58, I see it on the computer. So these are definitely worth memorizing, because these are kind of the cutoffs. If you get higher speeds in your flow than those numbers, then you have to assume compressible if it's below that. So this is really, could be called low speed flow. All right, so let's do an example that everybody has done experimentally. Everybody have a garden hose now, or grew up in a house where you had a garden hose? Right, so you turn the water on, the water shoots out the end of the garden hose, and it's not real fast, right? If you want to wash your car, what do? Yeah, you put your thumb on it to make the hole smaller, or you buy a mechanical device, it's called a nozzle, that takes the diameter of the tube and narrows it down. And from conservation of mass, we know that if the area goes down, then the velocity goes up. So that's why the nozzle is there. So here's an example. This is a pretty small nozzle. So 1-inch garden hose, 1-inch diameter, or a 1/2-inch radius. And the reason we need to know that is we need to know that area that's going to go into our formula. All right, and it has a nozzle. So here's our garden hose. This is 1 inch. And then the nozzle goes down. And this has a diameter equal to 1/8 of an inch. So typically in your book, the problem will be written like this. You have a 1-inch diameter garden hose that you bought at Sam's Club. It's the Members Mark brand that says it's kink resistant and kink free. And you get it home and you put it in the front of your house and it kinks up all over the place. Does that sound like something I've done? Yeah, I have a hose and the thing kinks all the time. Okay, so the problem doesn't include all that other stuff. It says a 1-inch garden hose and it has a nozzle that's put on the end that's 1/8 inch in diameter. What did I do over here to the right of that? What is this? It's a picture or a figure, right? Just like in dynamics, you drew free body diagrams. In this class, draw a picture labeling the different points in the flow where you know stuff. And that helps you think about the problem. You look at the flow, you look at the areas, and you go, oh, yeah, I think I'll use conservation of mass. So in the homework, whenever you're given a word problem like this, draw a picture. And I will actually grade that. I will look for the picture and give you points for drawing the picture. Now, we haven't done that up to this point because like the homework that you're working on now says at a point in the atmosphere, the pressure is this value and the density is this value. I guess the picture that you could draw would be right? And so I've kind of haven't emphasized drawing pictures yet because we haven't really started talking about flow going through things. But if you cannot all draw a picture, draw a picture. All right, what's the fluid? I haven't said, have I? Liquid iron. Compressible or incompressible? That's going to be some serious garden hose if it can handle liquid iron, right? Is it what?
I said I like my idea better.
What was your idea? Grape juice, so that works. So, I mean, that could happen, right? We're at a winery and they have a tank filled with grape juice and they need to transfer it to another tank to make wine. So I haven't said, so we need to know more information. This is going to be a garden hose, so you would almost assume that it's hooked up to the city water supply, right? Although not necessarily. It could be mercury. That would work. It wouldn't melt the hose like the liquid iron would. Well, what would you use? You'd have to use like a ceramic or some other metal that would not melt at the temperature of liquid iron. All right, so we look at this and we go, okay, it looks like we're going to say that the flow velocity V1 Rho 1 is here. And there's going to be an area A1 here. So I'm starting to label the variables that I need. These are the fluid variables. I have a velocity, a density, a pressure. And then over here we have a velocity, a density, a temperature, and a pressure. So what do we want to do with this? Well, right now it's not stated in the problem, but what we want to do is we'll find out how much faster. Oh, whoa, 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 there's not ones over here. How much faster is the velocity here than here? How much speed up do we get? So we want to find the ratio of V2 to V1. So that's the problem. So we draw the picture. We label the flow variables. Well, there's some flow there. There's some density, pressure, area, density, temperature, pressure, area. We want to know velocity differences. What do we know in this problem? I haven't given you the pressure. I haven't given you the density or the temperature. So what do we know or can we calculate? We can find the areas, right? Because I gave you the dimensions here. So you guys do this. What's the area 1? What's the area 2? I guess we ought to decide what units we want to use. It's given in inches, so let's find the area in inches squared and see if we're going to be okay. So what's our area A1? Somebody shout it out. Pi. And R is? So what is that number? .785. Do I understand you right? Did I hear that right? Okay, how about the other area? It's going to be pi times 1/8 divided by 2. So what do we get there? You have to shout it out loud. 0.012. Did you guys all get that? Is that good? All right, so we know areas, and then we go, all right, what equation do we know that has areas in it? How about ideal gas? P1 equals rho 1 R T1, that's really the only equation we know so far, right? That we've used. No, I don't see area in there. I see pressure. I don't even see velocity, so that's a bust. Then we go, yeah, conservation of mass. That has area in it, and it has velocities, right? Rho 1 V1 A1 equals rho 2 V2 A2. Assumptions, 1D steady. Now we go, okay, I want to know V1 and V2. We're looking good. There's V1 and V2. We know A1 and A2, so we can check those off. We know that, and we can solve for this ratio, but I don't know the density. So I'm going to assume an incompressible flow because it's going to make the problem easy, right? No, the reason we assume incompressible flow is that it's water. So you have to say that, assume incompressible flow, which means that rho 1 equals rho 2, so you can cancel those out. So all that's left to do now is just ratio these two numbers. So what do you get? Somebody punch that in. So V2 over V1 is, it's going to be A1 over A2. So what do we get? Somebody have that? That's because I solved that equation. I moved the V1 over there, the A2 over the other side. Actually, I can calculate the answer. I made you do this stuff, but we can actually just ratio these two, right? And the 1/2 cancels out with the 1/2, and we get 1/8 squared. So it's 64. So that's decent. The flow coming out of the nozzle is 64 times as fast as the flow coming in. So that's how you use conservation of mass with the assumption, and then you can solve a problem. So what is the value of V2? How fast is the flow coming out? I need to know V1, right? So how does this problem, how is it going to know V1? So there's a change in velocity. We're saying the velocity here is a lot faster than the velocity here. So if I have your car and it goes from 10 miles an hour to 100 miles an hour in 10 seconds, what causes that? Fundamentally, physics. Acceleration from what? A force, right? So looking at this, the velocity goes 64 times as fast. There's got to be a force causing that. What's the force? In the fluid problem. There's not a 250 horsepower engine driving this, right? Like a car. There's not a jet engine. What is the force that's going to drive a little piece of fluid right here down the pipe and go screaming fast out here? Do you see a force variable here? The pressure. So there's a pressure here and a pressure here. That's density. Pressure here. So what that says is the only force available is the pressure. So there must be a pressure drop from here to here because there has to be a net force to accelerate that fluid. And so to solve this further, we need another equation that talks about pressure difference and velocities. So that's the second principle, which is Newton's law for fluids. And what is the force? It's going to be a pressure drop, pressure difference. And what's the mass? It's going to be the density times the volume. And what's the acceleration? It's going to be the change in velocity over time. And so that's the equation that is going to give us the relationship between velocity so that we can solve that extra question we have. So really we'll need to know, well, what pressure does the city supply for the water supply? And then out here will be atmospheric because that's where the water's coming out the other end. But we need to do this. So this is next. All right, so next time we'll start that. We'll also do an example of air that's a compressible flow, and I'll show you how you can solve that problem. But I have this real quick video I want to show you. So I'm new to showing videos on Zoom, but let me see if I can make this happen. Let's see, I'm in full screen mode, so I didn't go full screen for that. All right, you guys can see that on the screen, right? This is final assembly of the 777 aircraft, done in 7 minutes, 6 minutes actually.